Challenger.
Welcome, viewer. Today, we'll be looking at a challenge video. Obviously, I have been told multiple times that all my debunking and videos are shit, and been given this video that completely proves the earth is flat. I just had to take the bait, as all the flat earthers keep mirroring each other's work. It was a bit hard to find the original. I think I found it though. The claim is beautiful in its simplicity. Here is a photo taken from Winter Hill near Preston, looking past Blackpool Tower beyond the Irish Sea. And we see the Marilyns of Isle of Man. With the distance involved, with the curvature of the earth, those should not be visible. We are even presented with an elevation chart explaining how it should all be hidden. Really, just look. In all seriousness, out of all the so-called proof I have came across, this one is truly one of the best. Now let me present you with, let's say, my hypothesis. With the photo in hand, before we start calculating how much should be visible, shouldn't the first question be how much is visible? How much are we seeing? Yes, I appreciate that it looks big, but I'm really bad at large-scale estimation. Maybe there is a way. Well, fortunately there is. Unfortunately, the best image quality I could get was from the video itself. That is only 1080p. I will reach out to the original channel to see if you'd be willing to provide me with a better quality image to do the same analysis. Why does that matter? Well, we'll be doing some calculation, and it's nice to be a bit more precise. Let's run through the idea on how we can calculate from the photo how much of the hills we are seeing. The technique is really simple. We need one item with known height and distance. This will give us a viewing angle. And we need the pixel height for that item with calculated viewing angle to get our pixel to degree ratio. It goes without saying that viewing angle is independent to distance. Now suppose an object on the photo has a viewing angle of 30 degree and occupies 300 pixel, which means an object with 10 degree would occupy 100 pixel, regardless the distance between these two objects. That is a simple linear scale. Note, I do appreciate lens distortion, and that happens to every lens. This distortion is however minimal near the center line. Thankfully, this photo doesn't appear to be taken by a large wide-angle lens, and then the distortion, finger crossed, should be minimal. Now to calculate the visible height for an item with known distance in the same photograph. First, we get the viewing angle from pixel height, then the angle with distance would give us visible height. So that's the idea. Back to this Isle of Man photo. We have our vanishing point at horizon line. Here is the first problem with the quality. Due to the fuzziness, I'm not sure if I got it right, but to give flat earthers a better chance, I will go lower than where I think the line is. For illustration, I have drawn lines with 3 pixels, but I'm using guide when it comes to actual measurement. So one line for vanishing point. For our object with known height and distance, we have the Blackpool Tower in view. Here is another point of error. The tower itself is surrounded by a small building, and we cannot see the actual base. From the photo, we'll have to guess a little bit. First, I got a 4K photo of the tower. You can see the original on screen. Next is to resize and overlay on top of the Isle of Man photo. I think I did an okay job with this. Again, due to low quality, I'm trying to be as close as possible to the top of the tower for another line. finally guessing where the base of the tower would be. This is our third line. One more line for the top of any of the hill. Let's choose the one near the tower for more accuracy. Before the math, one quick thing to note. The distance between Rivington Road and Blackpool Tower is 39.5 km. We are told the eye level is at 286.5 meter and Blackpool Tower height is 158 meter. Which brings me to, yes, I completely understand that a photo from high altitude looking down would create a perspective distortion which would be more prominent the closer the object is and would appear to be leaning. But here, a difference of around 130 meter over 39.5 kilometer. Well, I think we can ignore the distortion. In fact, the tower still looks okay, right? Just to illustrate what we are doing. To get the viewing angle to pixel ratio, we don't need the whole tower. Using vanishing point as a guide, we can calculate the angle made by the visible portion above the horizon using right angle calculation. So, not the whole tower, but the part above horizon. From our overlaid image, we can get a pixel value of from horizon to top of the tower and another pixel value for horizon to the bottom of the tower. From our actual height of the tower, we can now say in meter value of how much is above horizon. This is our opposite leg. Distance is obviously adjacent leg, that is 39.5 km. We can now get adjacent angle, which is spanned over visible portion in pixel value. Let's start. If 378 pixel of tower is in reality 158 meter, 293 pixel would be 122.47 meter. Adjacent angle is arctan of opposite divided by adjacent. So that is arctan of 122.47 meter divided by 39.5 kilometer. Don't be a Nathan and make sure that units are all the same. That brings us a value of 0.178 degree. So 293 of pixel area covers this much of viewing angle. Now to calculate the angle for that hill. Our hill has a pixel height of 127 pixel. So the viewing angle for this hill would be 0.077 degree. Once again, this is the angle between horizon to viewpoint and top of the hill to viewpoint. For our adjacent leg, we have been given a distance of 144.03 km. This can be another variable prone to error. We really need the distance to the hill we're measuring. So another assumption I would have to make. In Google Earth, using my guess, I get a distance of 143 km. But let's go with given value. Height of visible part of the hill would be tan of angle times adjacent leg or the distance in this case. That brings us to a value of 193.56 meter or 635 feet. I'm pretty sure that the math is sound. The only issue is getting the right pixels. I had made several assumptions. I tried to draw the horizon line lower than where I thought it should be. I drew the hilltop line higher. I guessed where the tower base is. Finally, I'm not sure the exact distance to the hill or exactly which Marilyn we're looking at. The Isle of Man contains 5 Marilyns. My guess is our view is between North Barrel, that has an elevation of 561 meter, and Snaefell at 621 meter. Finally, let's jump to an Earth curvature calculator. Observer height is 286.5 meter. Target distance is 144.03 km. Without any atmospheric refraction, 548.8 meter should be hidden. This is where I think I will meet most of the resistance from flat earther. Sorry guys, atmospheric refraction is a fact. If I remember, I will try to link my previous video talking about this with many examples. From top of my head, twinkling stars, color when sun is near horizon. On that video, I also explain how this all supports atmospheric refraction. In this video, I refuse to get into that discussion. Now with standard atmospheric refraction of 0.1671, our hidden value becomes 396 meter. So the hill we're looking at has a total height of 396 plus our calculated 193 meter, which brings us to a 589 meter height, which falls between Nordbergville and Snæfell's height. Let's write down the full formula. The only reason I expanded the formula so we can see what the dominance values are. Our estimation of visible tower over horizon has the least influence. But I do feel guilty. Tell you what, let's go crazy, favoring flat earth. The higher the visible altitude of the hill, the better it is for them. To do that, we can increase the distance. Now I already gave them 1 kilometer, but let's give them some more. I drew a path going past all the hills. That gives us a distance of 152 kilometers. We can also reduce the pixel value of tower height over horizon. How about if we give them 10 less pixels over there? Finally, let's give the hill a bit more pixel height. I'm sure I gave it a couple of pixels to begin with, but 10 more, sure. With all that, 152 kilometer times tan of 137 times arctan of 122.47 meter divided by 39.5 kilometer divided by 283. As I mentioned earlier, visible height of tower is least impactful due to being divided by known distance. I hope it makes sense. To recap, we increased our distance by 9 km. We reduced tower pixel height by 10 pixels and added 10 pixels to hill height. Even with all this, our new value is around 35 meter more than before. I am aware that adding 228 meter to 396 meter gives us 624 meter, which is higher than Snæfell. And I will leave it here for flat earthers to jump on. They need this. But my point here was to illustrate that all the assumptions I made while drawing the horizon, top of tower, base and such, the final error margin is not really that much. Again, a higher quality would be so much better to calculate. I believe this brings the video to a satisfying end. Hopefully I managed to illustrate with math that what we see is perfectly explainable on a globe Earth. Moving on. Thank you so much for watching. If you have liked this content, please do like and comment. And if you can also subscribe, that would help my little channel grow and would be thoroughly appreciated. Have a safe day. Signing off.
Try.